Let's talk about Kirchoff's laws. So someone asked me to make another video. This is something that you should always do. If you don't find the support in the videos that I posted adequate, please ask me to make another video. And I looked, the video's pretty old, like 6 years old. So here's a new video, Introduction to Kirchoff's Laws and Some Applications. So first of all, when we have one battery and a set of resistors, we can usually solve the circuit just using what we know about series and parallel resistors and Ohm's law. But once you put two power supplies or two batteries in a circuit, it often becomes impossible to solve without using Kirchoff's laws. And in fact, Kirchoff's laws can be used to solve any circuit. So there are two of them. And when you study circuits, if you take a circuits course, they use the short acronym of KVL, Kirchoff's voltage law. And it says that the sum of all voltages around a closed loop have to equal 0, and it's called the loop rule. So you'll see when we do a circuit, if we go around a loop of circuit elements, the voltages, positive and negative, have to sum to 0. And that is based on the law of conservation of energy, because voltage is related to energy, the law of conservation of energy. Any energy that enters that is supplied by a battery has to be taken out by the resistor. Energy has to be conserved. So when you go around a closed loop, the sum of the voltages have to be 0. And you'll see what this looks like when we apply it to a circuit. If you come to a junction where a wire splits and goes in two directions, sometimes called a node, then the currents into the junction have to equal the currents out. Or another way of stating it is the sum of all currents at a junction, going in being negative, coming out being positive, have to sum to 0. The currents in have to equal the currents out. And that is based on conservation of charge. If a charge goes into a junction, it has to come out. Charges can't be created or destroyed. If cars go into a tunnel, they have to come out. They can't disappear. And that's called the junction rule. Okay, so let's look at a circuit that we wouldn't be able to solve other than Kirchoff's laws and apply these two laws to that circuit. Okay, here's a circuit with 3 resistors and 2 batteries or power supplies, and we'll use Kirchoff's laws to find the value of the current through each resistor. And so one of the first things that you do once you've drawn the circuit when you're using Kirchoff's rules is to label all the currents. So notice that resistor 1 has a current in it, and whatever that current is, it's going to divide. So the current here and the current here is going to be different, and the current through R2 is going to go here and divide. So because the current in each resistor is going to be different, the only way it wouldn't be different if there was no current through here. Then there'd be one current. You would have a simple series circuit. So none of these resistors are in series or parallel. The way I've drawn it, you might think they're in parallel. But if 2 resistors are in parallel, they have the same voltage. So you can see that if I put a voltmeter here at these 2 points, I'm going to read the voltage across this resistor, and I'm also going to be reading the voltage across this battery and this resistor. So they're not going to have the same voltage, and the same way here. So the voltage across and the current through, let's just review that for a second. This is a bit of a digression, but it's important. If I want to read the voltage across this resistor, I have to hook up my voltmeter this way. right? Because you always read a voltage between 2 points and always use the word across. If you want the current through the resistor, so the voltmeter is in parallel, right? We didn't have lab this year, but in lab it would be very important to learn how to measure the voltage across a resistor. You put the 2 probes on either side of the resistor and you measure it. If you want to measure current, you have to open the circuit up. You have to undo the circuit, create, oh, I can't erase that, create an opening, and then insert in series an ammeter. So you insert the ammeter here, and the reason the ammeter has to be in series is so any current that goes through the resistor goes through the meter. They're in simple series, because if the current were going here and the ammeter were here, then current through the resistor and through the ammeter would be 2 different currents. So, all right, so that's an important digression. Let's go back to the circuit. So I erased the meters and I put in values for the resistors, and just to keep it simple, I made R1 1 ohm, R2 2 ohms, R3 3 ohms, easy to remember. I made the voltage of V1 4 volts and the voltage of V2 6 volts. And then, so what we want to find out, what we're after here, what we don't know is what is the current through each resistor and the voltage across each resistor, the current through and the voltage across. So let me write that down. So there are actually 6 things we don't know. We don't know the voltage across all the resistors, and we don't know the current through, and so I've labeled them this way, and just so I don't have to label this VR1, just to save writing, I relabeled this VB1, V battery 1, V battery 2, and so V1 refers to the voltage across R1, I1 is the current through it. And in your diagram, one of the things you always do, and you should be drawing these circuits, is to label all the currents in the diagram. So the first thing you're recognizing is that there are 3 and only 3 different currents. And a current always starts at a junction and ends at a junction, right? If there's no junction, the current in a single line, a single element, a single loop has to be the same. So I1 starts here, goes through the battery. Remember, current does go through the battery, just like water goes through a pump. Goes through this resistor and gets to this junction and then ends. I3, the current through resistor 3, starts at the junction and ends at this junction. And I2 starts at this junction, goes through the battery, goes through the resistor, and ends in this junction. And if you've had a circuits class, you may have other methods for solving it. You should, in fact, learn this method. It's better to know more than one method. So in circuits, they sometimes label this I3 differently, but you're going to see we're going to eventually get there. But we're starting very simple. We're recognizing that there are 3 currents. Now, notice I gave a direction to the currents that seems logical. But what do you mean logical? Could the current be in a different direction? It could be. You see, this is a 4-volt battery. This is a 6-volt battery. How do we know that this battery isn't going to force current backwards through this battery? And in fact, if this were a 16-volt battery and this were a 4-volt battery, it almost certainly force the current backwards. So how do you choose the direction? You choose the direction using your best guess, and you'll know whether you guessed right or wrong, because if you're wrong, it'll come out negative. You just need to be consistent. Let me write that down. So these are the steps you want to follow. Draw the circuit, label the currents. We did that. And when I say label currents, give a name to each current. This is a simple one. There could be 5, 6, 10 currents. but we won't do circuits that complicated. So in this circuit we have 3 different currents. We've labeled them and we've shown their direction. Labeling the currents means you have to show their direction. You'll see in a minute why that's important. If you label the direction wrong, it won't matter because the mathematics will tell you you're wrong, because the current will end up being negative, indicating that you got the direction wrong. Now, it looks like we have 6 unknowns, but once we get the 3 currents, because we know the resistance, we can easily calculate the voltage, right? The voltage across resistor 1 will be the current through 1 once we have it, times the resistance of resistor 1, and so on for the other 2. So really all we got to do is solve for the currents. And so we need 3 equations, 3 unknowns, and we're going to get those equations by using Kirchoff's laws. Okay, so we've drawn the circuit, we've labeled the currents, now we have to write the 3 equations. Okay, when I look at the circuit, I'm going to show you there's 5 different equations we could write, but you'll see they're not all different. There's a junction here, so we can write a junction equation for this junction, or we could write a junction equation for that junction. There's a closed loop here, so we could write a loop, a voltage, a KVL, Kirchoff's voltage rule, loop rule equation for this loop. There's a loop here. And you can go around the loop any way you want. You don't have to go with the current. You'll see that in a minute. But usually we go with the current, go around the loop this way. And then there's actually an outer loop. So there are 3 loops. So let's write the junction equation for this junction. So the currents in equal the currents out, or the sum of the currents have to be 0. So our junction equation, go ahead, write the junction equation for that. And come back, and then write the junction equation for this. So write those 2 junction equations. So what I did was I went here and I write the currents in first. So I1 goes in, I2 goes in, I1 plus I2 go in, I3 comes out, I get this equation. If I go down here, I3 goes in, I1 plus I2 comes out. You see they're the same equation. So we don't actually get 2 different equations. We only get 1 equation out of the junction rule. So now we still need 2 more equations to solve for 3 unknowns. So go to the loop rule, and let's pick the right-hand loop going in the direction of I2. And the left-hand loop going in the direction of I1. Go around the loop and label all the currents. Pause the video, write the 2 loop equations, and then come back. Do the best you can on your own. Don't worry about making a mistake. Just try. Okay, see how you did. So starting here and going around the closed loop back to this point, we get VB1. And there are some sign conventions that you have to learn. When you go from the negative terminal to the positive terminal, the voltage goes up. When current goes through a battery, the voltage drops. And so the voltage drops here. So this has to be a negative voltage. From an energy point of view, the battery puts energy in, the resistor takes the energy out, this takes some energy out, and when you get back here, the sum of the voltages or the energies have to be 0. If we started here and went the opposite way, when you go around a loop, remember, you can't always follow the current. So if we went around this way, we have to reverse the sign of this. This would be positive I3R3. How do we know that? We're moving around the loop opposite the direction of the current. We would move around the loop opposite the direction of I1. This would become positive, and we would go backwards through the battery. And if there were a situation where current goes backwards through the battery, you're actually charging the battery, you're putting energy into the battery. So it makes sense physically and mathematically. The other way of thinking about it is if you take a voltmeter and you put it here with the black lead, we weren't in lab so we didn't do it, and the red lead here, it will read 6 volts. If you reverse the leads, it will read -6 volts. And the same way, if you put the black lead up, if you just move the meter up here, where the black lead now goes here and the red lead goes here, and you measure the voltage across the resistor that way, you would in fact get a negative voltage. So you do have to know and follow those rules when you write your equations. Here are your 3 equations. The rest is algebra. So, drawing the circuit, not so bad. Labeling the currents, that's important. Make sure that you do that right. Writing the 3 equations, just follow the rules, but you do have to know the sign convention. Solving the equations is, I think, the hardest part. Doing the 3 equations, 3 unknowns. If you know linear algebra, you can do that. I'll show you what I would do. I'm not going to do all the algebra. It's very, very easy in a case like this to make a mistake. But I'll show you what I would do. And if you have better methods, that's fine, or different methods. So the first thing I would do would be to rewrite the equations. So VB equals that, right? I'm going to move the 2 negative quantities on the other side of the equation. So I just rearrange those equations. Then I'm going to substitute in I1 and I2 for I3. So we would have R3 I1 plus R3 I2. Same thing here. R3 I1, right? I'm just substituting this parentheses of I1 plus I2 for I3 and distributing the R3, so R3 I2. Now I've eliminated R3 and I have 2 equations and 2 unknowns, I1 and I2. So this would combine so that you would have 2 I1s. So you would have R1 plus R3 I1 and R3 I2. You could continue to solve this in general, or you could combine those resistors and put a number in. And then you're going to do the same thing here, but in this case the I2s combine, so you would have R3 I1 plus R2 plus R3. Hope I didn't make a mistake already. I2. And then you have to take, I would take these equations and make a common factor so I could subtract one equation for the other and eliminate either the I1 or the I2. Or you could solve for I1 and I2 and substitute it in. It is messy and complicated, so I'm not going to go further. That's more algebra than it is physics.